Any questions on the homework assignment before we get started with today's lesson? Now, today's lesson, kind of like yesterday's lesson, is going to be a lot of kind of older stuff that we've done before. It's not going to be a whole lot of new stuff. Because the first thing we're looking at are these two here, the fundamental theorem of algebra and the linear factorization theorem. The fundamental theorem of algebra implies that a polynomial equation of n degree has precisely n solutions in the complex plane. We have at least one. If it's a polynomial function, we have at least one solution in the complex plane, no matter what the polynomial function is. So really, what that means is even if we had a linear function, which gave us a solution of x equals 4, still has a solution in the complex plane. It just means it's just 4 plus 0i. So we can make any number a complex number, so therefore any polynomial function will have at least one solution in the complex plane. So it doesn't mean it's an actual complex solution where we actually have a value with I. So we can have x equals 4 plus 0i. Now from this theorem, it also states that if we have a polynomial of degree n, where n is greater than 0, f has at least one solution in the complex plane, or more specifically, we can go from this and say that the degree is equal to the number of solutions. So if it's a degree 3, it has 3 solutions. If it's degree 4, it has 4. And it's one of the ones that we did like from Algebra 2. Now the linear factorization theorem, so if we do have a polynomial function, has precise n's linear functions, we can rewrite the polynomial function in factored form. Essentially each of the solutions as factors multiplied together. So this first one here, the first degree equation x minus 2 has exactly one solution because the degree is 1. And it works out the solution x is 2. The second one here is a second degree equation. Since the degree biggest exponent is 2, it's a second degree. So it has 2 solutions. It just works out that the solutions are both 3. Even though we have a repeated solution, we do count it twice. And the last one here is a degree 4. And it has to have 4 solutions because it is a 4th degree. And it works out that the solutions are 1, negative 1i, and negative I. So the degree is equal to the number of solutions. Now, if we're able to get it down to a quadratic, we can use the quadratic equation because it does help us find complex solutions. And it does work out that one specific part of this is helpful. It's not using crayon. And that's everything inside the radical. What we call this is the discriminant. Now the discriminant b squared minus 4ac helps us understand what kind of solutions we'll get. Because if the discriminant is positive, we'll get 2 real solutions. If it's equal to 0, we'll get exactly 1 real solution. And if it's less than 0, we'll have 2 complex solutions. Now the reason that for greater than 0 and less than 0 we have 2 really comes into this here, the plus or minus. Because whatever value comes out of the square root, that plus or minus is going to make it positive and negative. We'll have 2 different values. We have 2 different options. So you don't have to write this next part down. I'm just picking values. So if we said what came out of this here, b squared minus 4ac was, say, 9, well, that does simplify to 3. We have 2 values. They're not rational. I mean, we could have any number because it could be rational. It could be irrational. But whatever comes out of this, we will have 2 solutions. And they're both going to be real numbers. Doesn't mean that they're going to be nice numbers because we could get the square root of 3. Square root of 3 is not a nice number. But if it is 0, negative b plus or minus the square root of 0 over 2a, well, we know the square root of 0 is still 0, which really is just showing us that we have negative b over 2a. Now it does say one solution. Again, in Algebra 2, those that took my class for Algebra 2 I like to say not really one solution. Actually, I like this. It's one repeated solution, because there are still two solutions. They're just not unique. Because in Algebra 2, I would say it has one unique solution that's repeated. So whatever the value is going to be there twice, because we still have two values for that point, but it's only going to be one number. And the last one is if it's less than 0, well, that just means we're taking the square root of a negative number. And if we take the square root of a negative number, we're going to end up with, all right, so we're going to end up with two complex solutions, the positive and negative case. And we also know from the complex conjugate theorem, which we'll cover again today, if I have one term with I have to have a second. Complex numbers always come in pairs. Irrational numbers always come in pairs. If I have the positive I have to have the negative. If a plus bi is a solution, a minus bi has to be a solution. We can't have one without the other. So, the first set of problems we're doing here, we're wanting to use the discriminant to determine the number of real and imaginary solutions. That's it. That's all we're doing for these here. We're not actually solving them. We're not trying to find the values. We're just wanting to see what we will have. And the discriminant is our b squared minus 4ac. And especially with quadratics, this is sometimes helpful to look at. And in this case here, b is negative 20. 4a is 4, and c is 25. And when I look at this here, if I was going to take a guess, there is a good chance that we could end up having imaginary solutions. And the reason I say that is when I look at the second half of this, let me get a highlighter. Is there any way that negative 4ac is going to be a positive number? Well, no. So there's a good chance we could end up with a negative when we multiply this out. But at this point here, we don't have to do this by hand, because we can say 20 squared minus 4 times 4 times 25. Actually worked out to be 0. Questions on this here? Questions on why I didn't put negative 20 squared instead of just having 20 squared? Because we know negative 20 squared should give us the same thing as 20 squared, so we can drop the negative. That's what I normally do. Because if you do put negative 20, you need to put it in parentheses. Otherwise, it will give you the wrong answer. It will tell you that it's negative, I believe, 800 instead of this here. So this here is 0, which means we have one solution, one unique solution. We still have two technical solutions. They're just the same number. Questions on this here? So if we look at the next one, b squared minus 4ac. So we have 7 squared minus 4 times 13 times 2. I have a feeling we're going to have two complex solutions. What do you think is going to be bigger, 7 squared or 4 times 13 times 2? Well, 4 times 13 is 2, carry the 1, 52. That's going to be bigger, most likely. And we can double check and make sure. 7 squared minus 4 times negative 55. And again, I said doing this is sometimes helpful, especially if we're trying to solve these. Knowing this here, that there's a good chance that that's not going to give us a nice number, give us complex numbers. I'm not going to even try to start factoring, because we can't factor nicely with complex solutions, and especially if they're irrational. Because we got negative 55 for this, yes? Well, in the quadratic theorem, we'd have to take square root, which would mean we would have I, and the square root of 55 does not come out to a nice number. So could we factor it? Yes, but most likely for us to be able to factor it, I would need to actually know the solutions. So that almost most of the time when I factor these here, I end up getting the solutions and then working back to the factors. So this is too complex. Questions on this so far? We good with this here so far? And the next one's going to be two real solutions, mainly because any type of problem set that we have like this that we work through, or we have three possible choices that could occur, we end up getting one of each. And if we look at this here, b squared minus 4ac. Well, b is negative 8 minus 4. A is 5, and what's the value of c? Is there a c? Yep. Because it's going off of ax squared plus bx plus c. So we're adding c to it. Since there's not a constant term there, it's understood to be 0. Anytime it's missing, a term is missing, it's understood to be 0. Well, that whole section 0, 8 squared is 64, so we have two real solutions. Questions on this here? Any questions on any of this so far? Not too bad. A lot of just a recap of Algebra 2 again. So, x squared plus 2x plus 2. We want to write this in standard form, and standard form is considered to be a plus bi. Now, we're probably going to need to either use completing the square or the quadratic formula. We're going to have to use one or the other. Two reasons I say that. One, it tells us to write complex solutions in standard form. And since the degree of this polynomial is 2, we know we'll have 2 answers. And if we do have complex solutions, they always come in pairs. So it's kind of leading us down to the fact that the 2 solutions for this should be complex. Also, with factoring, if we look at it that way, a is 1. So really, we're trying to see what factors of 2 will add together to be 2. Well, we only have 1 and 2, and they add together to be 3. So it's not going to work. Now, it doesn't matter which one we do, because we could use completing the square. Completing the square would work for this here, or the quadratic formula. I like the quadratic formula a little bit better, because here everything is equal to 0. It's just throwing the values of a, b, and c in and solving from there. So here a is 1, b is positive 2, and c is positive 2. X is equal to, so we have negative b. Well, that's just going to be negative 2. Plus or minus the square root of 2 squared minus 4 times 2 times 1. All over 2a, or 2 times 1, which is just 2. Questions on this here so far? At this point here, I would start using the calculator a little bit, because there's a good chance. So we'd have negative 2 plus or minus over 2 square root 2 squared minus 4 times 2 times 1. We could probably do that in our head, or just as easy to plug it in, and we get negative 4. Now, yes, this one here we could have plugged into the graphing calculator. If it's in a plus bi form, it would have told us that it's 2i. And the reason that it does work out nicely is because a 4 is a perfect square, so it would simplify it. But we still need to simplify this here, because the negative is going to come out as I, and the square root of 4 is 2. Now again, since I said standard form, they wanted an a plus bi form. I did not make y'all do that in Algebra 2. I just took this here for the most part. If you notice that it did simplify, we would simplify it. As we saw the other day, especially with dividing where we got 2 fractions, that is a plus bi form. That's our actual standard form. Here, luckily it is very nice because everything does simplify. I'll go on and write it out so that we see it, because really we're saying this here split across into 2 fractions. In Algebra 2, I would just say, well, we can divide everything by 2 and simplify that way, which just tells us that we have 1 plus or minus I, and that's our final solution. Questions on this here? Questions on anything we've done so far? That's pretty much a rehash of everything you've done before. I mean, probably it's having to kick some of the dust off of those memories, but it maybe had a small desire that they would never show up again. But questions on this here? Do we feel comfortable with using quadratic formula? Okay. I don't feel like seeing another one of these is going to make any difference than what we've already done. Complex solutions occur in conjugate pairs. If a plus bi is a solution, a minus bi is a solution as well. Now, this can be helpful, especially on the ACT, because they will give you, sometimes they'll give you higher degree polynomial functions and ask you to find the solutions. If they give you an imaginary solution, we have to have its conjugate. So if they told you x is equal to I, x is equal to negative I has to be a solution. We have to have, if we have one, we have to have the other. They always have to come in pairs, which is kind of helpful. Now, for most quadratics and higher degree polynomial functions, for those of you who had me in Algebra 2, the first thing I would do, even for something like this here, is I would graph it. I would graph it, because if what we're trying to find is what values of x will make the function equal 0. It's where it crosses the x-axis. So for this here, we could go in here, x to the 4th, my short-term memory, minus x squared minus 20. Because if this crosses the graph 4 times, those 4 would be the solutions. Now here, we can see it crosses twice, yes? So we do have 2 real solutions. Most likely we'll have 2 imaginary solutions. Which tells me, especially on the ACT, if any of the solution set or choices, answer choices, have all 4 real numbers, they're not going to be it. And we could check them on the graph. Especially if they give you answer choices, you can go through here and find out, are they actually solutions? Do they make a y value of 0? If they do, they are. If not, they're not. And you can cross them out. But for this one here, we're going to have 2 complex and 2 real solutions. This factors. I have a feeling most of y'all don't see them. And that's fine. There's nothing wrong with that. I've done this way too long. That's why I can see this factors, and also I set these lessons notes up, so a little bit cheating. Most of us are not used to factoring something that has x to the fourth and x squared. So we're going to use a little cheat. And what that cheat is something called u substitution. I'm going to substitute u in for a term, and more specifically, I'm going to substitute it in for x squared. And this is used a little bit in Algebra 2, not a whole lot. We don't focus on it too much, but especially when you get to calculus, they use it a lot more because we can make something that's more difficult to try to solve and evaluate into something a little bit easier. And what this does for us here is, well, for one, we can turn the middle x squared into just u. Now, x to the fourth, well, really this is the same as saying x squared squared. U squared minus u minus 20. Is that something that y'all could probably factor? A lot easier than x to the fourth minus x squared minus 20. Because if we look at this here, two sets of parentheses with three spaces. Now I look for the signs. And I always reference it back off of the third term, the negative 20. If it is positive, the signs are the same and match the sign of the middle term. If it's negative, the signs are opposite. Well, the 20 is negative, so we'll have a positive and negative. Because the only way to get a negative number is multiplying a positive and a negative together to get that. What are the factors of u squared? Well, u and u. Only way we get u squared. Now we're going to look at the factors of 20. 1 and 20. 2 and 10. 4 and 5. Which ones do we want to use? Because we're trying to get a middle value of negative 1, yes? So 1 and 20 is probably not it. 4 and 5. And since it's negative, we want the bigger number to be negative. Questions on this here? Any questions on anything we've done so far? Well, we do have two things multiplied together equal 0, so one of them must be 0. So we're either saying that u plus 4 is 0 or u minus 5 is 0. Now I could have plugged it back in the previous step. I sometimes feel splitting it up equals 0. We can plug it back in because we're really not solving for u, we're solving for x. And u is x squared. A different color. I'm going to write this out to the side. Because really what we said with this previous statement that x to the fourth minus x squared minus 20 factors to x squared plus 4 times x squared minus 5. That's how it would factor. But sometimes using the u substitution does make everything a lot easier to work with. And now that we have it down to here, we just need to solve for the value of x. And what's nice about this is that both of these equations don't have a middle term. The value of b is 0. We don't have x to the first power. So we can use the square root method. Subtract 4 from both sides, telling us x squared is negative 4. At this point here, we would square root both sides telling us x is equal to plus or minus. Well, the negative is going to come out as I, and the square root of 4 is 2. So we have 2 of our solutions. We still need 2 more. So for the other side here, we would add 5 to both sides, telling us x squared is positive 5. And again, at this point, we would square root both sides, telling us x is equal to plus or minus the square root of 5. So here are our 4 solutions. Questions on any of this here? I have a feeling you might want to see another one of these. Luckily, I do have another one. And again, with this one here, we can use the U substitution to solve. Now, in years past, I don't think actually anybody's asked here. During my student teaching, I did have a student ask about using U substitution, the quadratic formula. Can we use those together? Yes and no. It gets everything a little funky. Because we would get a solution for U, but then we also have the fact that it's actually the same as x squared. So we'd end up getting x squared is equal to plus or minus square root of. So eventually we'll end up having to try to take the square root or try to solve this here. It makes it more complicated than it's necessary. But there's other methods and means to try to solve these higher degree and approximate. And luckily for us, we mainly work with ones that work nicely. And again, for this one here, I'd start out with using U substitution. If you're able to see the factors of it, awesome. Go on and factor it. But here, using this here, substituting U in, our x to the 4th is going to become U squared. Because of our x squared squared, we get this here. Our 7x squared is going to become 7u minus 18. Luckily for us, they're not going to have a greatest common factor, so we can move on to our 2 sets of parentheses with 3 spaces. Then we find the sign. So if we look at the third term, if it's positive, the signs are the same and match the sign of the middle term. If it's negative, our signs are opposite. Luckily for us, the factors of u squared are u and u. Now the factors of 18 are 1 and 18, 2 and 9, 3 and 6. 2 and 9, and the 9 would be positive, and the 2 would be negative. Which is really telling us that u plus 9 is equal to 0, and u minus 2 is 0. Now this one here would have actually given us 2 real solutions. Well, 2 integer solutions to be more precise. And the reason I say that is because once we get it here, we know that u is just taking the place of x squared. X squared plus 9 is going to have 2 nice numbers. We'll also have x squared minus 2 is equal to 0. Now we just need to solve. So here we can subtract 9 from both sides. Nope, I was wrong. I was hoping for 3, but it's not going to be 3. Well, not just 3. If we square root both sides, we get x is equal to plus or minus 3i. So close. Any questions on how we got these 2 here? Now if we do the same thing with the other side, we would add 2 to both sides. telling us x squared is equal to 2, bless you. Square root both sides, telling us x is equal to plus or minus the square root of. Questions on this here? Finding the zeros of a polynomial function. Yep, I think I included that again. Go back one. Yep. So we want to find all the zeros of this polynomial function given I plus 1 plus 3i is a 0. 1 plus 3i is a 0 for f of x. So that's kind of helpful. So we know 1 plus 3i is a solution. What else do we know is a solution? One minus 3i. Because if 1 plus 3i is a solution, 1 minus 3i is a solution. If we have one, we have to have the other. Yes? Okay. There's two ways we can go about this. We can go about it the mathematical way, or we can go about it a little bit different. I'm going to need another sheet. Because when I first looked at this, again, we didn't do it with the last one, but we did it with the first one of our fourth degree. I went on and just typed it in. X to the fourth minus 3x to the third plus 6x squared plus 2x minus 60. And hit graph. It crosses the x-axis at 2 nice points, yes? That's kind of helpful. And if we go second graph, I see that it crosses at -2 and 3, yes? So two solutions for this are -2 and 3. How many solutions should we have total? 4, because the degree is 4, yes? Do I have 4 solutions? Yes? Is that what they were wanting us to do? No. So we found all of them here. And I'll tell you this now, especially if there might be a problem or two like this on the homework where the degree is 3 and they tell you one of the solutions is I. Well, we know one of the other solutions has to be -I, yes? And as long as the third solution is an integer, positive, negative whole number, we can find the rest. Now, I'm going to show you what it really wanted us to do. Back up. This is what it told us, is that x is equal to 1 plus 3i. X is also equal to 1 minus 3i. Now what we want to do is get these equal to 0. So we would subtract 1 and subtract the 3i here. We're comfortable with doing that. Trying to get it equal to 0. So we would minus 1 from both sides, minus 3i. I know I didn't explicitly write it out, but are we comfortable with this here? On the other one, we'll do a similar thing. We'll subtract the 1, but this time we will add the 3i. Part of the reason we're doing this is we want to simplify this polynomial function down. And to do that, I'm going to divide. But to divide, we don't like dividing by complex numbers with complex numbers. So we want to find the polynomial function that has these solutions. So we're going to multiply them together to see what that polynomial is and then divide. So for this here, And again, when I worked this out, because I worked both of these out, I multiplied and then kind of set it up in a staggered step. We'll see it here in a minute. X times x is x squared. X times negative 1 is negative x. X times 3i is plus 3xi. We've done this before. Next one we did was multiply through by negative 1. And I kind of matched it up to its like terms. Negative 1 times negative 1, or sorry, negative 1 times x is negative x, like terms. Negative 1 times negative 1 is positive 1, yes? Wrote it out to the side. Because the terms that we have so far, none of them are a constant number, so I pushed them over a little bit, so like terms match up. Negative 1 times 3i is negative 3i. So I put them over there by themselves because, well, they don't have any like terms. They don't have any friends so far. They'll have some later. And lastly, we can do the same thing with negative 3i. Negative 3i times x. Line them up with his like term. Negative 3i times negative 1 is plus 3i. Negative 3i times 3i is negative 9i squared. Now you don't have to write it this way. You could have written it horizontally as one straight line and then combine like terms. I do it this way just, it's me personally. This isn't any written standard you have to do it this way. I like it because I can add things straight down. So x squared is going to come straight down. Negative x minus x is negative 2x. 3xi minus 3xi, this is 0. Here, negative 3i plus 3i is 0. What do we know about negative 9i squared? It's positive 9. I squared is negative 1, and negative 1 times negative 9 is just going to make it plus 9, yes? 1 and 9 make 10. And again, I was doing shortcuts in there, so if you want to write it completely out, that's fine. So we know two of our solutions is x squared minus 2x plus 10. And for all of you, when we did polynomial division with a divisor that had a degree greater than 1, we went with long division. It is possible to do it with synthetic division, but most of the time we just say use long division. We have x squared minus 2x plus 10 on the outside. Inside here is going to be x to the 4th minus 3x cubed plus 6x squared plus 2x minus 16. Now, one of the nice things with this here is whenever we divide polynomial functions, the degree decreases by the degree of what we're dividing by. So our starting polynomial is degree 4. What we're dividing by is degree 2. 4 minus 2 gives us 2. So our degree of the polynomial we should get is a degree 2. So the first thing we're going to ask is what times x squared is x to the 4th, which would be x squared. And we'd multiply that. We'd say x squared times x squared minus 2x plus 10, which x squared times x squared is x to the 4th minus 2x cubed plus 10x squared. And then we would subtract. X to the 4th minus x to the 4th is 0. Negative 3x cubed minus negative 2x cubed. Negative makes a plus. So we'd have negative x squared. Not x squared. X to the 3rd. 6x squared minus 10x squared is negative 4x squared. Then we bring down the plus 2x. And we repeat the process. Then we see what times x squared is negative x cubed. Negative x. And we do it again. We say negative x times x squared minus 2x plus 10. And luckily for us, we only have to do this one more time. So this would be negative x cubed plus 2x squared minus 10x. Plus these here would cancel. Negative 4x squared minus 2x squared is negative 6x squared. 2x minus negative 10 is going to give us 12x minus 60. Because the negative and negative in the center would make a plus, so 2x plus 10x is 12x. Are you comfortable with this so far? And the last thing is what times x squared is negative 6x squared? Negative 6. So we're doing negative 6 times our x squared minus 2x plus 10, which is going to give us negative 6x squared plus 12x minus 60. And when we subtract these here, the first terms do cancel. It actually works out that everything cancels, giving us 0. And we should expect that, because if it's a solution, it should have a remainder of 0. Which leaves us with this here, x squared minus x minus 6, which does indeed factor. And I have a feeling at this point you're running out of room. Yes. Which would be x minus 3. And I know I'm running out of time. Times x plus 2. Which tells us x minus 3 is 0. X plus 2 is 0. And if we solve, x is equal to 3. X is equal to negative 2. So we found our two other solutions. Does this kind of make sense on how this works? I know I went pretty quick through the last two solutions. But we're going to stop there for today. We have one more of this here, one more of a different type, and then we're done. So we'll do those last few problems tomorrow. Then you'll have the rest of the time to work on the assignment. And then we'll be done with 4.2.